The next example, we are going to look at this shear transformation. And let's take a look at this particular example. This transformation T maps R2 to R2, where A is this matrix. Let's find an image of this following square under this transformation, and this is the square. Now, how do we compute its image? This is what we do. So let's take a look at this image. There are 4 vertices, right? So let's label these 4 vertices. So this one will be let's call it, well, we try to avoid using A because we already have a matrix A. How about I just say this is my matrix. Take a look at vertex number 1, which is this point 0, 2. Okay, 0, 2. Now, under this transformation, let's do a little algebra. 1 times 0 is 0 plus 2, 3. So 1 times 0 plus 3 times 2, right? The second one, the second entry is the second row times this vector, because the second row is 0, 1. So it returns you the second entry, which is 2. So which gives you 6, 2. Now if you sketch that, this actually is this guy. So this 0, 2 is mapped to 6, 2. So that's the image of this point. Let's take a look at the other points. Say this point, okay? This is 2, 2. So 2, 2. It's going to be 2 times 1 plus 2 times 3. The second one is 2. So you get 8, 2. Okay. So which means this point is mapped to this point. This point is mapped to this point. So take a look at something that you want to take a look at is, what about the distance between these 2 points? This distance is actually the width, which is 2. And take a look at the distance here. So it is still 2, right? So, and then now for the other 2 points, 0, 0 should remain because anything times 0, 0 is 0. And for this particular point, let's do the very last algebra. 1, 3, 0, 1 times 2, 0 is equal to 2 times 1 plus 0 times 3, right? 0 times 3. And the second one is just 0, which is 2, 0. So this point stays the same right here. Now, what this transformation really does was just think about this square. It is being pushed from this side, So every horizontal line is pushed towards the right hand side. It depends on where this horizontal line is. If the horizontal line is in the x-axis, it stays the same. The higher the horizontal line, the further out to the right. So this is what this shear transformation does. It kind of like being pushed horizontally to the right. Of course, you can see that actually, in order for us to find the image of those points, we basically did a lot of those vector calculations. So this is the first one that we did, right? So this matrix times this vector. So this matrix times this column vector. And the second one is the same matrix but different vector. So oftentimes we can organize these vectors into columns and form another matrix like what we did here, so that after you do this matrix operation, so take a look at what would we get from for this the first column. You will get exactly the 6 2, right, which is the image of this vector 6 2. And the second one you'll get 8 2, which is the image of the second vector. And the next one is 2 0, which is the image of this guy, and the 0 0, which is the image of origin. So oftentimes we really don't have to do the algebra for so many times. We can just simply form a coordinates matrix, and then we just need to find its image by doing this matrix multiplication. So this is one example of the example of shear transformation. So in general, this K represents a horizontal shear. If it's positive, then it's shifting to the right, shear to the right. If it's negative, it's shear to the left. So this is what it does. I would like to have you also think about, just give a try, think about what this will do, what this new matrix will do, this transformation will do. So by like picking, say, suppose this is 3, this is 1, and what does it do? So use this square, and then you can check it out. And what about negative 3? So those are the things that I think I will leave you some room to explore. Okay. Now we are gonna come to this key definition, linear transformation. A few things that we really have. This is a very important definition. So what does it take for a transformation to be so-called linear? The first one is this. You transfer the image under T of U plus V, which means the sum of the two vectors, right? So the image of the sum of two vectors is equal to the sum of the image of each individual vectors. So this is what the first one says. The second one says T of Cu. What is Cu? Cu means you're stretching or shrinking this vector U. It's equal to the same amount of stretch or shrink of the image of U. So in other words, you can factor out the C. The first one means you can distribute the T. So these two properties together makes the transformation T being linear. Okay. Key important. So this is important property to highlight. The transformation, linear transformation, preserve the operations of vector addition and scalar multiplication. Geometrically speaking, it preserves the straightness. So a straight line must map to straight line. Okay, this has to be true. Straight line cannot be curved. So this is one very important property of linear transformation. So straight line, linear line remains linear line. Two useful results for the linear transformation. The first one is T0 is equal to 0, which means origin after the linear transformation, it is still origin. Okay, this one is just a combination. This one is just combination of these two properties together, and this can be proved really very pretty easily. So for instance, dv. So T of Cu plus dv is equal to T of Cu plus T of Cv, according to the property number 1, right? The first property, that's what it is. And now you can pull the C out according to the property number 2. D, this is D. D, T, V. Okay, so this is how we can quickly prove the second property. And the first property, T0 is equal to 0, can be proved by using, so 0 means 0 plus 0. And then according to the first property right here, we can actually distribute this in the T in kind of distribute the T. And then this is equal to 2 times T of 0, right? And this is the same as the left side is T of 0 vector. The right hand side is 2 times T of 0 vector. Therefore, T of 0 has to be 0, which proves this result. Now, let's take a look at other two transformations. The first one is called contraction, and it is defined by this. Tx equals r times this vector x, where r is a real number. When r is from 0 to 1, this is so-called contraction. When r is greater than 1, it is dilation. Now, first of all, let's let r be 5. Let's show that this is a linear transformation. And what does it take for a transformation to be linear transformation? Basically, these are the two properties you want to show. So, for instance, let's begin with, say, T of u plus v equals, according to this definition of the linear transformation, it should be equal to 5 times u plus v, right? Because it says T of x equals 5 times x. So this is my x. So 5 times x equals, now I can certainly, according to the vector operation, I distribute this 5. And what is this? This actually is T of u, right? Because T of u will be 5 times u. And similarly, this will be T of v. Do you see that T of u plus v is equal to T of u plus T of v? So we show the first property. The second property is T of c times u is equal to 5 times c times u, according to how this transformation is defined, which is 5c times, which is c times 5u. We can swap these two constants. And what is this guy? Isn't that T of u? So we actually check the second property. To find the image of the square under this T, I'm gonna just show you say how to find the image of this particular vertex. I believe you can find all the other ones. So in this case, this is T of this vertex, which is 2, 2, equals, according to the way it is defined, it is 5 times this particular vector, which is 10, 10, right? So basically, this is what the image of the 2 and 2. If I draw a graph, I'm gonna find a place to make a little graph. So suppose this is the square, this is 2 and 2. After this so-called dilation, it becomes 10, 10. So this point goes to this point. And please verify that origin stays the same. 2 goes to here, this 2 goes to here. Basically, it enlarges this square by a factor of 5.